Rules of inference are, well, they're basically logical structures that are always true. So here's what they are specifically. The first rule of inference says, hey, if you have this scenario, so if P then Q, you also have a second if Q then R. Anybody have a guess what the conclusion should be there? I know it'd be kind of difficult to type, so let me actually go ahead and throw it in. The conclusion here is that you can string those two if-then statements together and get, if you started with P, following the little arrows, you can get all the way down to R. This is a super, super, super common thing that we do in math and in any logic of you have a whole bunch of if-then statements and you string them all together. Okay? Now, that being said, there's another way that you can use if-then statements. Suppose you start off with an if-then statement and you know that if P, then Q is always true. Well, then somebody tells you you have P. What should be the conclusion here? Anybody have a guess? This one's way easier to type. If you know for sure you have if P, then Q, and you're also told for sure you have P, what are you going to get? Yeah, you should definitely get Q, as one of you answered. And this one actually has a Latin name that goes with it called modus potens. I don't care if you remember that or not, but if you wanted to know the fancy name, there's the fancy name for this one. Okay. Now, there is a second way of using this stuff, and it goes as follows. Suppose you again have an if-then statement, so you know for sure that if P, then Q happens. But this time, instead of being told that you have P, what you're told is you for sure, definitely 100% don't have Q. Any guesses what you should logically infer from that information, or those two pieces of information? This one can also be relatively easily typed. So what do you guys think? Throwing this out to you guys. Yep. So as one of you guys sent in, this would then mean that you get not P. In other words, if there's no way you were able to get over here to Q, well, you don't have that Q. There's no way you could have started with P because you're told right here with this if-then statement, if you have start inside of P at all, you're going to get to Q, but you didn't get to Q, so that means you couldn't get to P. Okay? This here is actually, even though it has the fancy Latin term of modus tollens, this is actually using the contrapositive statement. The contrapositive statement says, if not Q, then not P. So it's using that contrapositive. Okay? Now, there are, actually, I'm just going to go ahead and skip to the next slide because I wanted to focus in on this one. And we'll skip out on the example at the end of that slide. You'll see it when I post it because there's not a good way to get rid of it. But so bridging off of what we just said in terms of those two guys, the Latin names, the modus potens and the modus tollens, this actually jumps us into some of the ways that we deal with explaining why something is true, namely proof writing in math. Okay? So there's a couple different types of proofs, and the first one is totally based on that modus potens thing, that where if you have P, then you have Q. Well, if you know you have P, you have to then have Q. In other words, it's called the direct method. And what this does is it simply links together all of your little logical statements. So it links together if P, then Q, if Q, then R, if R, then keep going. Okay? This one here is the one that we'll use the most frequently in our class. It's also, for a lot of people, one of the easier ones to figure out. That being said, it's so versatile that the only reason it's easier in our class to figure out is because I only give you very small examples. Now, the second type of method is something called the indirect method. This is what your book calls it. Almost nobody else calls it this. This is also called a proof by contrapositive. So what it does is you show that some statement. In mathematical statements, almost always have the form of if P, then Q. And if they aren't written that way, you can rewrite them in that format. And I'll show you how to do that in a little bit. It'll either be later today or the beginning of tomorrow. So what you do here with the indirect method or the proof by contrapositive is you show that that if-then statement is true by first saying, hey, I can't do a direct method on this because of whatever the reason is, and we'll go over an example like this to show you why you wouldn't. But what you would do is you say, all right, well, let's assume that this conclusion is false. In other words, we're assuming that we don't have Q. Then we look at our contrapositive, and we say, hey, we're going to have the negation of P as well. This is based off of the slide we just saw a second ago. This is using our modus tollens. Make sure I spell that correctly. Tollens, 2L. So those are two really, really common guys to look at. Now, the next one, and this is one that we're not going to look at hardly at all in our class. Depending on time, we'll look at one example. Proof by contradiction says you assume something, you walk through, and then all of a sudden you realize that there's no way that that works because maybe you get something like 2 equals 3. Okay? Something that would not happen if you're just dealing with integers. The next one after proof by contrapositive is actually dealing with counterexamples. Counterexamples are not proofs. Ish. Counterexamples are ways to show that your statement is not true. So it's actually disproving something. Remember, when we want a statement to be true, we're really talking about a tautology, so we need it to be true in all cases. The counterexample would be showing that you have at least one situation where that statement is false. Okay? So it wouldn't be the tautology. The statement wouldn't be true in general. We're not going to get to that today. We'll probably get to that tomorrow. And then the last thing is mathematical induction. This is a very, very specific type of explaining why something is true. In our class, we'll look at it in respect to when we have an equation or when you have some sort of formula, is it works beautifully, and we'll look at this at the end of this week. Okay? But for today, we'll look at the direct method, and then depending on time, we'll look at one example of a proof by contrapositive. And if we run out of time before we get to our contrapositive example, we'll do that tomorrow. So let us jump in to how you would deal with this direct method. The direct method goes as follows. You're going to be given some if-then statement. Then you want to actually show that that if-then statement is true. Well, the first thing that you want to do is you want to identify your two statements. You want to identify your if statement, your hypothesis, your then statement, your conclusion. Then the actual method goes as follows. You rewrite what it is that you are given in the actual problem. So you're going to rewrite your if statement, and let me actually put that right up here at the top. So write out the if part of the statement. Now, when you write out the if part of the statement, you then want to go ahead and say, all right, well, the if part of the statement told me the stuff that I'm given, the stuff that I'm assuming is going to be true in my situation. Then you got to say, all right, well, what does that mean I really know? So this is where you're going to use any definitions that we know. We're going to use any facts or theorems that we know to say, all right, well, with this stuff that with our starting point, how can we transform this into something that may be useful later on? And we'll have several examples of this. Okay. Then what you want to do is you want to use logic or our rules of inference to actually link all of the information together. Okay, so it's very much going to be like building a computer program. Okay, you got stuff at the top where you define all of your terms. You then start linking all of this stuff together. Don't skip steps or it doesn't work. Okay? And then lastly, once you've done all of this, you're going to state the conclusion of what you're supposed to get to. So notice the very first sentence and the very last sentence are given in the actual statement you're asked to prove. It's all the middle stuff we have to fill in. All right. Now there's a little bit of background information, and this is definitions that we'll need for the specific examples that I've chosen for us to deal with proofreading. This background information is just a couple of definitions. Okay? The first one is the definition of divides. The definition of divides is very, very precise, so watch out for this. It only is applicable to integers. So suppose you have two integers, a and b. A divides b if b equals a times some other integer k. Now, I should have just said some integer k. It's totally okay if k actually equals a. Now, notice what this thing divides means. This is exactly the same thing as saying in more layman's terms that a is a factor of b, which is often what you see at lower level courses, especially when you're dealing with integers. Okay? So that's the first thing. Now, symbolically, I already wrote it. Should have just looked ahead. Symbolically, this is written as a divides b. Please note this guy is not a fraction. So this a divides b is not the same thing as some fraction a over b. Okay? Not a fraction. This is simply just a symbol that says, hey, this little vertical line here represents the word divides. It's like shorthand, not actual mathematical symbols. It's more logical shorthand. So that's the first thing. The second thing is the definition of even. Now, we've actually already talked about the definition of even, but I went ahead and put it here again just as a reference. Some integer a is considered even if a can be written as 2 times some integer. Notice here, this is exactly the same thing as saying 2 divides a. So, or 2 divides a. Or 2 is a factor of a. The other definition that we need is an odd number. And again, we've talked about this one before. An odd number is an integer where a, the integer that's supposed to be odd, equals 2n plus 1 for some integer n. Okay? Again, this guy here, you often see it with 2n plus or minus 1. The official definition is with the plus 1 right there. And then lastly, we're going to need the definition of a perfect square. We looked at this, I think, on Friday, but I don't remember if I wrote it down or not. Definition of a perfect square can be given in 2 different ways. This is one of them, and I'll write down the other one as well. So an integer n is considered a perfect square if the square root of n is also an integer. And often dealing with the square root is actually not helpful. So the other way of phrasing this is an integer n squared is a perfect square if n is an integer. Notice what I did right there. I just squared both n and the square root of n. So that second way has a tendency to be a little bit more helpful. Questions so far? Kind of okay so far. I realize we haven't really done much yet. We've just done all the theory. So let us jump to an actual example. So here's the first example, and this example says we want to prove that the sum of 2 odd numbers is even. Please note odd numbers and even numbers are both integers. So you totally could have included the word prove that the sum of 2 odd integers, is an even integer. Either way, they're all going to be integers. Now, when we're doing this, there's a couple things that you have to worry about. First thing you want to worry about is rewriting this in an if-then statement. So any guesses what we're going to start with here? What would be the thing that you would know as a starting point versus the thing that's going to be the conclusion? Sometimes it's easier to figure out what the conclusion is before your starting point. Sometimes it's easier to figure out that hypothesis, that starting point first. Anybody have a guess? Don't worry, I'm totally waiting for you guys to have a guess. Yeah, so the starting point here would be that you have 2 odd numbers. Now, anybody have a guess on what the conclusion is supposed to be? Okay, so we've got an example of what would happen here, and that is a perfectly good example of what would happen. Now, here's the fun part, because that actually gives me a great jumping off point for a comment. In this particular case, if we tried to do something like a chart of all possible combinations of 2 odd numbers and then finding their sum, how many pairs of odd numbers are there that we would need to check? There are a lot. Yeah, there's actually infinitely many. I'm sorry, guys, you cannot actually go through all of them in your lifetime. And this is one of the reasons why we actually do proofs when we're in math, because we get into these situations where we have literally infinitely many cases that we need to check, and we're like, yeah, nope, that's not possible. I have to do something smarter. And that's where these proofs came into play. Because people always check examples first to say, hey, do I even believe if this statement is relatively sane? Okay. So first thing is we said we needed two numbers and they needed to be odd. So I went ahead and called the two numbers A and B because I didn't want to write two numbers are odd, that whole little thing over here to the side. So this is, if I was actually on a board or a piece of paper, this would totally be the scratch work to the side. If you're doing it on your own, maybe this is something where you have a sticky note next to you. Okay. Now, in order to get to the conclusion, we've got to know what that conclusion is. So if we're looking at an if P then Q format, let me actually write that up here, if P then Q format, we still have to figure out what our conclusion is. Nobody has said it yet. Anybody have a guess on what the conclusion might be now that we know that we're going to use the symbols A and B for our two odd integers? What are we looking for? How would we know when we've got what we want? Don't overthink it. There's a buzzword in that statement that tells you what you're trying to shoot for, what your target is here. Yes, far more detailed than what I was expecting, but yes. So the key buzzword there was the sum of the two odd numbers is even. So what we need is we need that sum, that A plus B, to be even. And what you typed in, yes, is totally what we're going to actually need to get to in terms of the symbols. Okay? So let's start putting this together. The first thing that you do when you, and we're going to do direct method here because that's the only one we've talked about. So the first thing that you want to do, especially if you don't have any of the symbols actually written down here, is you determine your symbols and then you need to write that out. So here we'll say, all right, well, we need to pick two odd numbers. And here we say, suppose that A and B are odd numbers, or if you prefer, odd integers. Okay. Now, we've done two things in this introductory statement. One is we've told our reader that we're using the symbols A and B to be our odd numbers, and the other one is writing out that hypothesis, that original starting point. The two key things. Now, second thing that we want to do is we want to go ahead and say, hey, you know, the only thing that we know right now is that we've got two odd numbers. So we just talked about a definition of odd numbers, so let's go ahead and write out the definition. And I went ahead and wrote out the definition of odd numbers for both of them. I've got here A is 2 times something plus 1. B is also supposed to be odd, so B is 2 times something plus 1. Please note that 2 is only being multiplied by those two symbols. And to complete the definition, you'd say for some, put in whatever letters you use, have to be integers. Now, quick check. Why did I use K and T? In other words, why did I use two different symbols right there? Anybody have a guess? Don't overthink it. Although, to be fair, it is a little bit subtle. Any guesses why two different symbols for K and T, as opposed to just using something like, I don't know, K for both, or N for both, like our definition used? And just as a heads up, it didn't matter what letter you used there. What mattered was that they were different, and that they weren't A or B. Ooh, you're close, but no, it's not a positive-negative issue. So, ooh, there's a longer thing. Yes. So, the question that you guys can't see, that answer that came in that you can't see, is actually exactly spot on. But this here, if A equaled 2K plus 1 and B also equaled 2K plus 1, that would actually mean that A and B were the exact same odd number. Now, there's no problem with A and B being the exact same odd number, but is there anything in this particular example that requires those two odd numbers A and B to be identical? This might be easier to answer for you guys. What do you think? Is there anything in that original sentence that requires the two odd numbers, A and B, to be the same or to be equal? And it's a yes/no answer. Anything up in that first sentence that requires A and B to be equal? Got one vote for no. What do the rest of you guys think? Is there anything requiring A and B to be equal so far? All right, so far I got 3 votes for no, and that's correct. There's absolutely nothing right now that's requiring A and B to be equal, which means you really, really, really have to use 2 different symbols, and these 2 different symbols allow your A and your B to actually be 2 different odd numbers. Now, it's still totally cool if they're the same odd numbers. K and T actually would be the same in that case, and that's fine, but this now allows your A and your B to be 2 different odd numbers. Now, once you go ahead and you've got some symbolic expression for integers or odd integers A and B, then you start looking towards your conclusion. And remember what your conclusion is. You were looking for your sum to be even, okay? So the next thing you can say is you can just say, hey, you know what? Let me go ahead and actually look at this sum. So any guesses what we would do when we start looking at A plus B? What would we do at a next step? Don't overthink it. Remember, logical induction or logical inference, you're building a little bit each time. So what should we do with this A plus B? We want to rewrite it as something. Yeah. So in terms of what we want to do, and I'm going to do it for you guys in a little bit, in a couple of steps. So the first thing that you want to do is you just go ahead and plug it in, okay? So you just plug in the expressions for A and B that we already have. Watch out with proofs. One of the things that we do, especially when we start grubbing around here in the algebra part, is we want to show each of the steps. So this here clearly shows that we are plugging in for A, we are plugging in for B. Now, as soon as we have that, that is obviously combine the like terms together. So this is 2k plus 2t plus 2. And we wanted to get that the sum was even. What do you think? Does that thing look like it should be even, that 2k plus 2t plus 2? And you could have used different letters than k or t. They just had to be different. So what do you guys think? Does that look like it might be even? So right now, it looks like it's relatively believable that this thing might be even. Now, how do we show it in a proof form that this thing is even? Well, this is the wrap-up to get to our conclusion. The definition of even was 2 times something. So you rewrite the thing that you know is even, and it is, as 2 times something. In other words, you need to find what that something is. Okay? So we now get it in our factored form. Now, definition of even said the 2 times something, the something had to be an integer. So you guys have worked with integers for years and years. What do you guys think? If you have some integer k plus some integer t, which may or may not be equal to k, plus 1, is this expression inside the parentheses still an integer? What do you guys think? Don't overthink it. Integer plus integer plus integer. Is it still an integer? Yeah, it is. So because this guy is an integer, you've got integer times 2. That gives you your definition of even, so let's write that out. So this guy is an integer since 1, k, and t are all integers. So that just wrote out what we talked out. And that says, using now our definition of even, we've got 2 times some integer. Thus, by definition, this sum a plus b is even. And if you want, you could say is an even integer. It's perfectly fine. And that would be our conclusion statement. Please know all of the colorful writing on this slide is scratch work labeled and unnecessary. The black writing in the middle, that's the part that would be the proof part that you would need. but I put in the extra comments there so you would see structurally the pieces and parts of the proof. Okay. Questions? Make sense? Could at least follow it when somebody else does it. I'm going to hope that meant yes. So, moving on to the next example. The next example that I've got for us is going to be dealing with divides. So it actually used the symbols, and I used the symbols at the top just so I could get everything up in one line. So how this reads is it says, suppose you've got integers a, b, and c, where a divides b and b divides c. What we want to do is we want to show that or prove that a divides c. Okay. Now, remember what divides means. Divides is the formal mathematical term that says is a factor of. So you could also read this as a is a factor of b and b is a factor of c. Prove that a is also a factor of c. Okay. So just like before, structurally we're going to do exactly the same thing. So the first thing that you want to do is you want to look at this in terms of an if-then statement, assuming it can be written like that. So the if part of the statement, that will all be able to be written as an if-then statement. So the if part of this statement would be the original information or the given information or the starting point information. Anybody have a guess what statement P is? In other words, the if part of if this guy was an if-then statement. In other words, what's the givens? Where's our starting point? What do you guys think? This is open-ended for you guys to take a wild guess. Or a guess. Hopefully it's rooted in logical information. Whoa, way more than I thought you were going to type. Yes, that would work. So the first sentence is the if part. Now, in this particular case, I went ahead and wrote it in shorthand because I had a very tiny little spot over to the side. So the if part that we're going to be looking at here would be, you got integers a, b, and c, and we are starting with the fact that a is a factor of b, and b is a factor of c, and pretend that q was not so horrible looking. Okay? Which means, what's our then part of our statement? And I on purpose wrote this example so it didn't, the sentence structure wasn't if, comma, then. Because often they're not. Although, more than half the time they actually are. Anybody have a guess what the Q statement here would be? Or the conclusion that we're trying to get to should be? Don't overthink it. Where are we trying to end up? So we're trying to end up at that second sentence. Notice the buzzword prove. The buzzword prove or the buzzword show are just going to tell you what you want to end up with. That's highlighting the then part of the statement, although some people put it at the beginning as well. So it's not always 100%. So in this case, our then part of the statement, if it was written as an if-then statement, would be we want to show or we want to prove that A divides C or A is a factor of C. Okay? So that's sort of our game plan. That's our broad strokes outline of starting point, finishing point. Now, that being said, we still have to do stuff. Now, this example is different than the previous example because it actually gives you all the symbols to use. So it already tells you use the symbols A, B, and C. We don't have to create that from scratch like we did in our last example. So when we start off here, we'll start off and just write that entire first sentence. You don't have to think about it this here, since that entirety of the first sentence was our if part when we converted this guy into an if-then statement. That's the entirety of our first sentence down here in the actual proof. Now, just like in the previous example, after we defined our terms and wrote out our hypothesis statement, then we were ready to go ahead and say, let's use some definitions to rewrite the information that we know. Now, right here, we've got three pieces of information. We know that A, B, and C are integers, and we're told that A divides B, or A is a factor of B. we're also told B divides C, or B is a factor of C. So the two things to rewrite would be these last two guys right here, where we want to rewrite those symbols, A divides B, B divides C. And this is where we would go back to our definition and remember that this means B can be written as A times something, and C can be written as B times something. Again, it doesn't matter what those somethings are, but just like with our last example, you do need to make sure that you tell your reader that the K and the T are integers. You could pick different letters, that's totally fine, but they need to be different symbols because that allows your B and your C to be different numbers. That's the key thing. It's totally fine if B and C are equal to each other, but you definitely want to allow the possibility that they actually are not, because let's face it, that happens more frequently. Okay? Now, any guesses what we might do next? Anybody have a guess of what we might do next? Well, not trying to be a trick question, this is sometimes the place where people draw a blank of what to do next. So I want to make sure that we're thinking about it. Anybody have a guess of what we might do next? Anybody have a guess on how you might determine what to do next? Not what it is, but how you might decide what the next step would be in something like this. So that perhaps is even more important than what the actual next step is. Ooh, good guess, but actually no. It turns out when you do these type of proofs, especially when you're dealing with the buzzword divides, that you want to avoid fractions at all costs. It turns out, while not wrong per se, all of the theorems, all of the facts, all of the definitions that we have are not written in the context of fractions, so it actually makes your life harder, and it excludes the case if t actually equals 0, which could sometimes happen. But it's a good first guess. We'll do something similar to that guess that came through. So one of the ways to figure out what to do next is you want to look to see what your goal is, okay? In our case, our goal is that we want to show that A divides C. Well, I'm going to do a little bit of scratch work here. How would we get to A divides C? Well, this literally means that A is a factor of C. So that tells you you need this guy. You need C is A times something. Now, we don't know what that something is yet, but that's the point where we need to get to in order to get this conclusion that A divides C. So at this point, we know how to rewrite C in terms of B's, not in terms of A's, and we know how to rewrite B in terms of A. So we're ready to go ahead and say, hey, you know what, maybe I can rewrite C now. So if we go ahead and look at C, we can say from the previous step that C equals B times T. Now, can we rewrite this expression right now in terms of A? Is there any way to get A in this expression? We can start plugging in. So what we'll do next is we'll replace the B in the expression with what B equals. And the nice thing here is B equals A times something. Okay? So we'll have that B is actually, and I put it in parentheses here, just like with the last example to show what the substitution was. Some people will go ahead and on each of these steps explain exactly what they did. I'm not going to ask you to do that, but do please put in some of these things like parentheses. That's the implicit way of explaining what you did. Now at this stage, what do we need? We still needed C equals A times something. So I'm going to regroup the parentheses to say A and then open parentheses something. Well, we already have what the stuff is from the previous line, so I'm going to say that A is really K times T. Now here's the big question for you. In the definition of divides, both of these two components have to be integers. The only thing we're really checking is k times t an integer? So what do you guys think? Based on what k and t equaled from when we used them up top, do you think the product k times t is an integer? All right, I got one vote for yes. What do the rest of you guys think? Is he right? Which I realize is the second question. So what do the rest of you guys think? Do you think that this product KT is an integer? Ooh, I've got one more vote for yes. Anybody else? I'm going to assume that the rest of you are thinking yes too, because yes, if you have two integers, the product is also going to be an integer, and I went ahead and just wrote that out for us right here. Okay? Now, since we have an integer here, and we had the a out front, and all of that expression equaled c, that's the definition of a divides c, or a is a factor of c. And if it helps, think of this as a as a factor of c, although I'll always use divides. Thus, we get a divides c by definition. I'm going to go back in and tag what we just did of each of those steps. That very, very first sentence was our hypothesis, and we use the symbols here that were already given. That second sentence was where we used the definition of divides. The third bit was where we did all of our algebra, and then we used the definition of divides to get back to our conclusion. Again, the colorful notation here is just comments and notation. The actual proof is just the black writing in the middle. Okay? But notice, structurally, this is exactly the same structure that we had in the last example. The hypothesis, so the if statement, plus dealing with any symbols, then use a definition to rewrite this information we were given, then do the part that's all this stuff that you might be thinking of was the proof to start with, but it's not, there's more. And then we have where we use a definition to get our math part, our algebra part, back into a format that we need, and then we're able to say our conclusion. Please note, with doing no work whatsoever, you can get this first sentence and this last sentence just by stripping them off of the given information at the very beginning, or the statement you're trying to prove at the very beginning. Some people do like to do the following. Some people like to work top to bottom and bottom to top, because why? Notice this actually gives you a little bit of where are we coming from, where we trying to go to, and then you sort of try to meet it up in the middle. An example the size of the one we currently did right here, it may or may not be necessary, but one thing I would recommend is always somewhere on scratch work, you write out, all right, what is it that I need to see in order to get to that conclusion? Has a tendency to be really, really helpful. Okay. The next example I've got for us to do is actually one of the activities, one of the examples I would throw to you guys. There's no way we're going to do that right now because it'll take a little bit longer than the 8 minutes we've got left. So I'm going to go ahead and stop us today, and tomorrow we'll start up with doing an example together. That's one of these proof writing guys. Okay? So any questions from you guys before we end out for today? All right. So I'll hang out for a little bit in case anybody has any